Welcome back everyone to the Hello World Guide. This is another episode of the Asteroids game in C++ series, and in this video we are gonna finally implement the actual asteroid to asteroid or polygon to polygon collision logic inside of our physics module. So in the last video we created a small test program or driver program to test kind of our polygon algorithm, and we could draw polygons and press the space key to test them. And in this video we actually will implement the intersects function. For this function we will use what is known as the SAT or Separating Axis Theorem algorithm, which will allow us to test whether two convex polygons intersect or not. It won't work for concave, but we'll get in that in a second. First let's implement the SAT or Separating Axis Theorem algorithm. For this, first of all, we'll create two variables called n1 and n2, which will set to the vertex count -1. The reason we subtract -1 from the polygons 1 and polygon 2 vertex count is because, if you remember, our polygons are implemented as line strip, which means that they contain an extra point to actually close the polygon, which is not an actual part of the real polygon from a mathematical point of view. It is just there to fix the rendering problem. So for that reason we will actually ignore the last point in both polygons. So we'll just create these two, n1 and n2, and we'll run a loop over n1. So we'll go from 0 to n1, and for each loop we'll calculate the normal vector. For the normal vector we'll first need to calculate the edge. We'll set the SI vector to f edge is equal to polygon 1 I dot position, the actual whatever current vertex position, and we'll subtract from that the next vertex position. However, we won't put this directly because this has the problem of going out of bounds. We can actually we need to actually use this modulus operator to get the remainder by n1, which means if it goes over n1 it will get back to 0, and we'll get its position as well. That will give us the edge. We'll create a vector called normal, which can be calculated by, for the x value of the normal we'll say negative of the edge dot y, and for the y value we'll just say edge dot x. Now of course this normal vector might not actually have a length of 1, it might not be normalized. We need to normalize it. For that we just need to divide it by its length. First of all we'll calculate the length using the Pythagoras theorem, for which we'll take the square root of the x multiplied by x. We'll square the x and y and we'll add them, and then we'll take the square root. And C++ by default does not have any exponential operator, and using a function here is unnecessary, since we can just say normal dot x multiplied by normal dot y, normal dot x again, sorry, and normal dot y multiplied by normal dot y. Then we'll take the square root of that to get the length, and then we'll just say normal divide equal length, and that will give us the actual normalized vector. Alright, now this vector has a length of 1. So we are going to go down here and we are going to create 4 variables, min1, max1 and min2, max2. So the minimum values are actually going to set to maximum in the numeric limits, and the maximum ones are going to be set to minimum. So this will actually help us implement the algorithm, and you'll understand the reason in a second. So for now we are going to have an inner for loop which will go over n1 again. So it will go for like till j is equal to n1, is less than n1 actually. So we'll just say for each of that iteration we are going to create a projection which we can calculate using this formula. We'll take the polygon's current vertex, according to j index here, and we'll get its x position, and we'll multiply that by the normal that we calculated here, its x, and then we'll add to that the y position multiplied by the normal y as well. So we'll do this. That will give us a projection, and we'll set our min1 to std minimum with min1 and projection. This ensures that unless our projection is infinity, it always set it to min1. The reason is that if our projection is infinity, it will be greater than max and it will set it to just max. However, if it's less than infinity, then since minimum 1 is infinity, it will automatically set it to projection. A similar thing going on for max 1 here, except that we are doing the opposite thing. Alright, so now we are going to basically copy and paste this loop, but this time we are going to go over polygon 2. So we'll change every instance of 1 to 2, including the min 1 and max 1. Now by the way, this algorithm works by determining if there is any axis separating the two polygons. If there is an axis, then that means that the polygons are not intersecting, and if there is none, then the polygons are intersecting. For checking whether there is an axis or not with our calculations, we can just check if our max 1 is less than min 2. Max 1, by the way, is less than min 2, or our min max 2 is less than min 1. If either of these is true, that means that there is a separating axis and the polygons do not intersect, so we are going to return false. If all of this fails and we don't return false, then in the end we are going to automatically return true, because that means that no separating axis was found, which means that they do not intersect. So now we'll go under by the way, oh sorry, this means that they do intersect. Now we'll go under main.cpp, and you can see we have already implemented the basic thing here, so we can actually run this and test to see whether it works or not. So I'm going to draw a basic polygon here with 4 sides and another polygon here, this time with 5, and if as I press this, you can see it says that they intersect. Now compare this, if I draw another polygon like 2 different polygons that do not intersect, it says do not intersect. Now I'm going to press space again, and I'm going to draw a concave polygon like this, where the angle may be greater than 180 degree. Now if I were to go ahead and create another concave polygon like this that does intersect, it will correctly detect that they do intersect. However, actually if I create this and I create this, then it again correctly detects that they do not intersect. However, if I were to go ahead and create a polygon like this and create another polygon that is kind of enclosed by its vertices, then it still says that it intersects, while they in reality do not intersect. So you can see that they are actually not supposed to intersect, while this is saying that they intersect. In reality they are not, because it's only meant to work for convex ones, and for concave ones it can have problems if the only intersection is kind of inside of the kind of this angle here. So yeah guys, this is pretty much it for this video. We have got an algorithm for convex polygons. However, we of course want an algorithm for concave polygons as well, but the problem is that we need to decide whether it is actually worth going through all of the effort implementing it for concave polygons, or breaking up our convex into multiple our concave polygon into multiple convex polygons and then using this. While that may be more accurate, it can provide a bit of a performance hit, and even though it should not be too difficult to implement and not too bad for performance, we can try it out and see whether it works or not. However, we can also kind of do a compromise and make our asteroid less concave, the angles are less extreme, so the chance of the asteroid going inside each other is going to be lower. And that seems like the wisest approach, since our game is a game and not a mathematical simulation. We do not require that level of precision. So anyways, we'll do that in the next video, so stay tuned for that. I'll see you in the next one, and make sure to like and subscribe as well, and share this video with other people, and I'll see you in the next one, and bye.